So today we're going to do a quick video on crystals and how to use them in your microcontrollers or other typical applications where they're used these days. Um, it's a pretty complex topic, and I'm not going to go real deep. And more of and how to maybe use the models that are in LTSpice. More of a, I think, as an educational thing. Um, I generally find it pretty difficult to create a good model from the data sheets that you get for crystals. Um, you can kind of make some good guesses, but you don't really know if you have a good model most of the time. Um, so what I did was uh, Microchip has this app note AN826, and they did this example crystal that they work with, and then they go through some formulas, and later, I think later down farther, they talk about how to calculate the load capacitor um, that are external to the crystal in most cases. Um, so one way you can do this is you can just put it in a spreadsheet, and I think I don't remember where I got this from actually, but you want to figure out what the external CL1 and CL2 are supposed to be, and this is how you would do it. The crystal data sheet would give you the load capacitance, and you would have your external capacitors and your stray capacitance, and those should equal, by that formula, the same thing as your load capacitance. And then you can also calculate the um, series and parallel resonance using a simple formula. And for the microchip example, um, plugging in these values, so they say FS 7.997 and FA, like they called it FA, anti-resonance. Get 8.013 megahertz. I think my microphone went off. Hopefully it's still working. Looks like it is. And plugging those into the spreadsheet, that's what you get. 7.9978, 8.03138. Okay. And if you do a SPICE model of that, um, you can do it two ways. Let me zoom in a little bit. You can do a discrete model and put in the values that they have, and or you can use their crystal symbol, which is really just a capacitor. If you right click on that, the parameters go into these locations, and so it's really just a capacitor that looks like a crystal that has some parameters added to it. And when you do that simulation on the I put in the 50 ohm resistors kind of out of habit. um, 50 ohms is kind of a common RF thing, and so if you do that and you do the the resonance and the anti-resonance, as Microchip calls it, you get 7.997 and you get 8.013. And interestingly, there's this point. So if you go here, that is, yeah. So now I'm not so sure. I thought I had, so sometimes the frequency comes out a little lower. We'll see how that works out when you actually put it in a circuit, which is the next thing I'm going to show you. So if you take that design and you put in your parameters and then do your external capacitors, and you do an oscillator circuit that looks something like this, it'll actually simulate, let's say, like 9 times out of 10. This won't always work for some reason. I don't know why. But then you take that and you zoom in on an area. So like this simulation actually ran, I let it run for almost 20 milliseconds. You don't want this stuff at the beginning. You want to just zoom in to an area towards just before where you stopped. And you can do an FFT on that transient analysis. And you use the current zoom, and if you just keep the defaults, it usually works pretty well. And OK. And here you go. Your peak is right here at about 8 megahertz. And we zoom in on that, and zoom in a little tighter, and we'll see that peak is 7.989, and but according to the spreadsheet, it should have been 7.997. So I mean, it comes out pretty close to where the series resonance is. So that's how that works. And I think I covered everything. Basically, here's how you calculate your external capacitors. Here's how you calculate the series and parallel or anti-resonance. And you can plug those things into a SPICE model and get the actually get it part of a transient analysis. And you can put the model into an AC analysis and get your Bode plots. The help file recommends that you use their composite symbol instead of individual components, as this simulates faster. Did I show? I did not show the LTSpice. So if you go into LTSpice, you'll and go to their help and look for crystals, this will come up. And they used different names on the model parameters, but they explained what everything was, and it's kind of annoying, but you can figure it out what values to put in where for your model. Anyway, I think I'm going to stop there. I think it's just kind of a fun thing to have as an educational thing, maybe more than anything else, because like I said, I don't know if it's easy to get actual accurate models for crystals. The data sheets give you some information, but usually you don't get like the inductance. And what else don't you get? I think they don't give you the motion capacitance a lot of times. So I think it's not particularly useful in designing a circuit, but it's really nice as an educational aid to help understand how crystals work. That's about it.